pin 7, you have no choice. That is C1 in A. That is the positive input of the op-amp comparator that's internal to the PIC32. There is an internal 1.2 volt reference that you can turn on for the negative lead. You can also map that to an IO pin if you wanted to, but we're not going to. Then we're going to put a 100 ohm resistor here rather than 300 ohms because, well, I'll tell you why in a minute. And then you need to choose this resistor so that you can get a reasonable value for the device under test, which will be the capacitor here. The output of the comparator goes to a pin called Cout. You're going to run that back into the input capture, which is another pin. So now that we've done that image, now we can go back and look at the connections. So the comparator uses positive input pin 7, negative input internally connected. So G1 is TPS output group 4, and could use RTP9, which is not in use otherwise, and therefore we're going to use pin 18. Pin 18 is then going to be wired to pin 24, which is the input capture signal. TPS input group 3. So what's going to happen is that when, logically what is going to happen in your program now is that your program is going to set pin 7 to be an output and set it low. That is now a low impedance source. It is going to discharge the capacitor through the 100 ohm resistor. You have to wait long enough for that voltage to reach near the ground. How close to ground can it get? How close to ground can this voltage get if this is the ground? Voltage divider. How close can it get? 100 over 100 plus R times VDD. So the lower this resistance is, the more accurately you'll be pulling this point down to ground. On the other hand, the lower this resistance is, the higher the peak current. The capacitor is charged up, and you suddenly ask to discharge it to ground, you're going to get a very large peak current. You can blow out the input pin. So 100 ohms is kind of a compromise. I'm going to ask you to discharge this point within 1% of VDD, with less than 1% of VDD. That puts a lower boundary on the value of R, of 100 times 100. So you're going to pull this point to ground. You're going to wait a while. How many time constants do you think you ought to wait? 5? I like it. 5. 3 is probably enough. 5 is certainly enough. So wait 5 time constants. Now we're talking, 100 microseconds. You're not going to notice it. Wait 100 microseconds or so. Make this an input again. Make this point an input. At the exact time, within a cycle or two, that you make this pin an input, start a timer. Just zero the timer and start it. So simultaneously, you make this an input, you start a timer. When this is an input, what's the impedance of that CMOS input? Is any current going to flow through that 100 ohm resistor as an input? The leakage current was that the CMOS at 3 volts is, it's glass, right? The gate is glass. It's really very high, it's probably 10 to the 12 volts. So no current, essentially, no current. Yeah, well, a little bit, no current to the flow. So this is an open circuit here. We just have an RC circuit that's being charged from VDD. We're going to get exponential charging. Sooner or later, this point is going to become more positive than 1.2 volts. And the comparator will change state from 0 to VDD. At that point, Cout will go high. That'll capture the device. What this capture device does is take the current timer that is attached to, running away, ticking away, and copies that value of the timer to another register, which you can then read at your leisure. So this input capture mechanism gives you a way of measuring cycle-accurate times. And one cycle here would be something like 20 nanoseconds. Once the capture has occurred, prudence would suggest you should take an interrupt to actually read the value. The input capture unit can generate an interrupt saying, I've got a value for you. You read the value, do a calculation on it, and that'll give you the capacitance. Because you know R, you're going to choose that in the homework. You know 1.2 volts. Actually, it's 1.2 plus or minus 0.06. So you're going to have to calibrate that voltage for your chip. How are you going to do that? The signal limit doesn't come to an output pin. It's not on an output pin. How are you going to calibrate that? Use the MUDAC. I think that'll work. Yes, I think you can actually route it to the ADC. Yes. And then what? So there's two pieces of that. Use a regulated voltage. set the circuit up, don't connect any of this stuff, put the regulated voltage here, slowly turn it up until change the state. Then turn it down until change the state, do that 2 or 3 times. You'll know within a few millivolts what the switching voltage is. But I like the ADAC idea. I just don't know how to do that, but there'll be a bit pattern that'll connect it. So you're going to calibrate this. You're going to choose this. You're going to switch back and forth between input and output. You're going to switch this to an output, 0 this point, 0 this point. Switch back to an input, watch the system charge until it reaches threshold, get an input capture. You know a time, you know the wave shape. I guess we should write that. So we're going to, if we look at the time curve, for some time before this, we're going to discharge this until we get down to 0.01 of VDD. This is not the scale. This is the voltage across the capacitor. At this time, we're going to do 2 things. We're going to make the pin 7 is an input, and therefore the system starts to charge. So it's VDD. And we're also going to start a timer. Sooner or later, we will cross 1.2 nominal volts. The input capture event will occur and store this time in a register. So we'll call this T1.2. It will store T1 time 1.2 in a register someplace for you and use the system ticks. And then, of course, you're going to take that and say that, well, 1.2 or whatever it is, after you calibrate it, it's going to be equal to VDD times 1 minus e to the minus t over tau. You know T, T1.2. You know the resistance because you're choosing it. You know everything you need to calculate C. We're dealing with real voltages here. The basic debugging tool you will use for this lab is the oscilloscope. So the very first thing you do when you hook this thing up and say, I'm not getting any capture results, is not to hold up your hand and ask the TA. Hook an oscilloscope to the capacitor and see what voltage waveform appears there. Question? Yeah. This? That's when you switch from output to input. You're switching 7 to an input and you're starting the timer. Yeah. That would be a good thing to do. Yes, it would. Yes, thank you. Yes, that would be a very safe thing to do. Would be to put a resistor between C1 out and the input, the capture input. As long as you have everything set up correctly, you shouldn't need to. But if you mess up and make that pin, what pin is it? It is input capture 1 is TP input group 3, TP 13 is pin 24. If you make pin 24 an output by mistake, boom, you blow it. Yes, you're quite right. There should be a resistor between. Now, the specs of the lab are that you are going to write the capacitance onto the TFT display, onto the liquid crystal display, formatted as capacitance equals XX.XX nanofarads. So you have to do some arithmetic to get the units into absolute seconds and absolute volts and all that sort of thing. For that, you may as well use floating point arithmetic. Don't try and scale this all. It's just floating point. It's plenty fast. You're only going to be making about 5 measurements a second because you can't possibly see anything faster than that. And so, since there's something like 1 million floating point operations a second, you won't notice. More questions? We haven't started talking about code to generate this yet. That's the next step. Oh, yes, yes. I was going to talk about timers next. Thank you for the feed-in. I appreciate that. See, you can use either timer 2 or 3 for this. There are 5 timers. Timer 2 and 3 are slightly more flexible than the others because they hook to more peripherals. So the timer 2 layout is fairly simple. Timer 2 is a 16-bit counter called TMR2 in TLive. That's the simple name, defined simple name. You can chain this, optionally chain this to timer 3, TMR3, to make a 32-bit timer. You have to decide which you're going to do. For right now, I will just talk about it as a 16-bit timer. The data bus can read or write this. There is a hardware equality operator. Now, this is hardware. It is separate from the CPU. It runs completely in parallel with the CPU. This is an equality operator which compares the timer with another register which you set called PR2. When they're equal, a couple of things can happen. The first is the timer register is reset in hardware. So the timer 2 is now a periodic counter with a period equal to the PR2 register value. Sits there, counts up to whatever PR2 is, resets to 0, does it again forever. You can also generate a timer event off of here. And I'm using the word event rather than interrupt because you can do more than an interrupt with this signal. You can certainly trigger an interrupt service routine, but you can also trigger a direct memory access event or a couple of other, you can trigger an ADD converter directly from it. But now, getting back to the question, the clock for this register comes from a prescaler. A prescaler whose input is, it's called TV clock, I think. It's the peripheral bus clock. The peripheral bus clock can be set to a different frequency from the CPU clock. The peripheral bus comes in here and it is divided by 1, 2, 4, 8, 16, 32, 64, and 256. So the first thing you should ask yourself is, what prescaler should you choose? And that's a hard question to ask. Because as you change the value of R in that circuit, the charging time is going to get longer and longer. If the charging is long enough, the timer 2 overflows, then you won't have a measurement. On the other hand, if you choose a small resistor, the system will charge very quickly, and if you've only gotten, say, 10 counts on timer 2 because you chose too big a prescaler, then you won't have sufficient accuracy. To get 1% accuracy, you have to have at least 100 counts in the register. Therefore, on the homework, there's another constraint on R, the resistance. The minimum R is 10K ohms, 100 times 100. But the actual value of R that you're going to choose will be constrained by having the number of counts in the timer be greater than 100 and less than 2 to the 16th, where it overflows. That is going to choose, so there's going to be an interaction, a non-unique interaction between the prescaler you choose, which sets the tick rate of the timer, and the value of R that you choose. The specification for the lab is that you're able to measure 1 nanofarad to 100 nanofarads. Only 100 to 1 dynamic range. That makes it easier. It is possible to do this lab without auto-scaling. Well, that's an interesting exercise. And how would you auto-scale? Change the prescaler. So the time output you measure here, this time, is going to be in system ticks. If the prescaler is set to 1 and the TV clock is set to 30 megahertz, then each tick of the clock is what? 33 nanoseconds. So if the prescaler is set to 2, it's 66 nanoseconds. So you get to choose the rate at which the clock ticks. I still want to say the clock ticks, the clock clicks. I almost can't say it. There's some sort of twisting. Everybody has to deal with their own twisted brain circuitry. So, we have a non-unique design decision to make here. That's the value of R and the value of the prescaler. Yeah. So, one way to do that, obviously, or maybe not obviously, is you have this event trigger into a service routine which triggers a counter. That's how I keep track of system ticks in the ProtoThreads library, which we haven't talked very much about, there's a millisecond timer, which counts the number of times that the timer has timed out, and uses that as the system clock. So the PD clock is phase locked to the CPU clock, and smaller or equal to the CPU clock. Yes. Yes. You have some recommendations on this. I've got some examples I'm going to show you, but that is a decision that you can make. We got 3 minutes. I'll show you how you set this up. There's lots to talk about here. Let's talk about ProtoThreads here. We go to the example 1 test code. And the very first thing in the test code, I'm going to have to put the screen down because I don't think I can reach over it. That doesn't sound good. So the first thing you do is include PLive always. Once you do that, then you can configure the oscillator using a C pragma. That is to say, a pragma is an extension to the standard GCC, which is specific to this CPU. And we're going to specify that the oscillator is the RC internal clock with phase lock loop. We're going to set CMOD to HS. That's a level of the clock driver. The phase lock loop input divisor, PLL-IDIV, is the phase lock loop input divisor. If you're using FRC PLL, then this must be set to DIV2. It must be set so that the output of the phase lock loop input divider is 4 megahertz. So this is set to 4 megahertz. Then I'm setting the phase lock loop multiplier to 16 with 4 times 16 to 64 megahertz. The CPU is running at 64 clock frequency. That's overclocked. I'll get to the sheet that always works. I think it will. If not, you have to drop this to 50 megahertz. But then the PV-DIV, the peripheral bus divider, is set to 2. Which means in this case, the peripheral bus is running at 32 megahertz. So every program you write will set up the clock. The clock is set in software, not by a crystal. Now, you can put a crystal to this device, and if you're going to use USB, you have to use a 12 megahertz crystal. But as long as you are happy with 0.9% accuracy, you can get along with the internal oscillator. 0.9% accuracy is good enough for RS-232 serial communication, by factor of 2. Is it good enough for a wristwatch? With a wristwatch that lost 1 second every 100 seconds, doubtful. So if you're going to make an actual stopwatch or a wristwatch as a final project, you would have to use a crystal, which is going to be about 50 parts per million, 0.005%. I strongly suggest going to the ProtoThreads page and read the example code. That's what we're going to start with next time. Questions about the homework, which is good, because it means people are reading it. The one question I got over the weekend was that table 29.9 in the new data sheet has been moved to table 30.10. However, if you just go with the link that's actually in the homework, then the table mentioned in the homework is correct. I almost hesitate to even say something like this because there might be the old joke about this crate has to be shipped upside down to avoid confusion. The top has been labeled bottom. It's just better to say nothing. But, any other questions? Now, one question just came up. I said in the homework, calculate R so that the number of ticks on the counter was between 100 and 60,000. That is the time to get to the threshold of 1.2 volts. So this time that you're actually measuring that is going to determine the capacitance has to be between 100 and 60,000 counts. What else?